Hello and good morning. Well, today I was in a contemplative mood, so I just started thinking about my Calculus 1 days and how we've taken granted of a lot of things. And I started thinking about the derivative of x to the power of n and how that's equal to n to the times x to the power of n minus 1. Well, I actually did find an interesting direct proof, sort of. I didn't do everything, but you can use combinatorics for part of it, but I'm going to present that today. I'm gonna skip some things because, well, I feel like if anybody's interested in this and they want to figure it out themselves, they can do it and they can fill in the gaps. But I'll give a rough map of kind of what I discovered. This is my first time. I'm not sure if other people have done this in Calculus 1, but I took a lot of things for granted. But here we go. So it's going to start off by the definition of. Okay, let's just first write the derivative of x to the n. As you've known, if you've ever taken calculus, that derivative of x to the power of n is equal to n times x to the power of n minus 1. And, that's really interesting. But, we tend to just start doing examples of this, and then, we take this and we just kind of fill in the blanks. It's just kind of plug and chug, essentially. Well, today, I kind of just want to look at the proof of why dx of x to the power of n is actually equal to n times x to the power of n minus 1. Well, I did find something. And, well, if you remember, ddx of some function, f of x, is naturally... I know a lot of people like using h, but I'm going to use a in this situation. Just makes things simpler for my brain to understand polynomials. So, as limit as a approaches 0 is equal to f of, you guess it, f of x plus a minus f of x all over a. So, of course, I'm sure a lot of people know this already. We use this in real analysis a lot as well, so that's pretty cool. So yeah, I'm going to do something here. All right, so let's just write that down, but for x of n again. So d dx x to the power of n is equal to, you guessed it, the limit of, as a approaches 0, of, well, x plus a. And you put that in parentheses to the power of n minus x to the power of n all over a. That's cool. I'm going to leave this here so you guys can look at that. We can actually expand this. We can expand this into a power series. I don't feel like having to... we could use sigma notation, but I'm not going to use that. I'm just going to say it's equal to the limit of a... limit as a approaches 0 of, well, you have 1x to the n, which cancels out with the x up there. And, well, we have some coefficient, b1. We're assuming that b1 is just, a element of the real numbers. And minus 1 plus b2 to the power of x to the... my damn pen. I don't like this pen. I don't like it much. N minus 2. We can keep going. The pattern just keeps going on and on and on, right? And, that goes all the way to a to the power of n. Again, you know what? I'll tack the minus x to the n at the end here. And, yep, that's right. That's all. Divided by a... Well, wait a second. These guys cancel out. Of course. Yeah, there we go. And is there a way I can make this thing go down? I kind of want to... Oh, okay. There we go. Okay, so, yeah, as you can see. Well, I guess the first thing is... I don't really feel like... Okay, so you have to ask yourself, what the heck is b sub n? Or b sub, I'm going to say m because we're using n. I don't want to make any confusion here. So from what I saw, there was a consistent pattern. Maybe you guys can find this pattern out yourself. By just going back and looking at x plus a to the power of n. I feel like people need to understand that themselves. So you get this c of m, and you also get this a, to the power of m. That's right. Apparently this is the pattern. So, but what does that mean up here? Well, if you look at b1, that's just c sub 1 times a times x to the power of n minus 1. But then you have to look at the other guys here, right? So if you look at b2, what is that? What is b2? That's right, it's c sub 2 a squared. So that means, well, if you remember any basic algebra, the a absorbs it. Each and every single a absorbs it, but they exist up in the numerator. So that means all of these, everything here, including a to the n over here, they all go to 0. Once you take the limit, they go to 0. So that means you are left with, you can't take the limit of the last one. Again, we're gonna substitute b sub 1, sorry. So that means we get, finally, at the end here, we get c sub 1 times a x to the power of n minus 1. Oh, sorry, this disappeared. This is gone. It absorbed the a, so that disappeared. So you get, so you get a c1. Now what the heck is a c1? Well, as you know, as you may have seen already, well, it has to be equal to n, right? What else would it be? And there is a way to prove that c1 is indeed equal to n. You can probably do a nice little proof of this. You can also see that when you multiply a polynomial, there will be n instances in which there are n instances of x to the power of n minus 1 for a given n, of course. So now you're asking, so that basically this C1 represents the number of instances of x to the power of n minus 1, essentially, without adding them together. Again, you can probably prove this. So I don't feel like doing that. I'm just doing a rough layout of what you guys can do. And there it is. There's n times x to the power of n minus 1. Isn't that wonderful? Anyways, I guess we can do like the little QED symbol over here. A little square with the scribbles. That's kind of interesting, I guess. I just thought I'd show this. Yeah, it was cool. I was having fun this morning, so yeah, I hope you guys enjoy this video. I hope you guys have a great day. Bye.